I could. So let's make sure this session is recorded and we are good to go. So once again, welcome back, guys. So glad to be with you. It's really fascinating class, but as you can all tell, it's not the same as previous sequences. Previous sequences of calculus classes like Cal 1 and 2, they were pretty much computational. This course is also computational, but it's different mindset if you have noticed so far. Things don't work the same as what they used to in Cal 2 and Cal 1. So, you know, equations they have different looks. The graphs have different looks. So it's kind of learning a brand new language. So the more time you spend on the course, the better understanding you'll have. But if you don't spend any time and you haven't even attended like homework number 1, then it will be challenging and, you know, it gets frustrating. And I hope you can find some time, to learn the topics because the course is just moving forward. Remember by first week of December, we should be done with chapter 16. I mean, that's mandated by the department. So, we have to do the best we could under the circumstances we are all in. So with that said, is there any question or any topic or any issue that you may have? Let me just take a look at the chat, see if there is anything. Are we doing a Zoom exam? Zoom meaning like I will be proctoring you? Is that what you mean, Ahmad? No, not really. So the exam starts at 5 and finishes like at 7, and you have 2 hours, and I'll just post the exam before 5 and it will be available exactly at 5. As a matter of fact, thank you for bringing that up. I'm going to make a mock quiz, which means a fake quiz with 2 questions on 2 pages. First question is, what's your name? Second question is, what's the date today? I just want to make sure that you guys know how to scan 2 pages as a single file and upload it on the Blackboard before the day of the exam, because I don't want to run into technical problem during the exam day. So I'm going to post that sometimes, let's say not today, tomorrow. And then don't panic. It's not like it's a major quiz. This is just a testing to see if you guys know how to scan and print and upload your solutions to Blackboard. Let's see. Hello, Charles. Because of the funds to kicked off the class. Oh, okay. All right. Sorry to hear that. And so as of now, we have 19 people. But those of you could attend, I really appreciate, and I am grateful that you could attend. So hopefully you will benefit from the live lectures. I hope you are also watching the pre-recorded videos. Those are like basic essential tools of what each section is about. So it will be nice to, prior to the class, like what Nick does, watch the videos. So then when we meet up live, we can get to nitty-gritty of the section. So the basic steps are, concepts are out of the way. So now let's see what's behind the scene. So that way we don't spend much more time on basic formulas. Well, anyways, so with that said, is there any question before we begin? Any?
Professor?
Hello?
I guess Raquel Mendez is trying to enter the meeting, but the link's not working.
Is that right? Well, let me see. The link, if you go on Blackboard, you should be able to kind of go through the Blackboard on Zoom, no? Let me check.
She said she needs the password.
Password is Cal3, CAL3, Cal3. Yeah. So that's CAL3, Cal3. Anyone else? Let me see if I have any emails from anyone. Okay, Kevin. Okay. So that's not it. And then, okay, these are not about accessing, these are about something else. Very good. All right. So are we okay now? Is everyone okay? So we good? Are we all in? Well,
Yeah, she was able to get in.
oh, great, great. I'm glad that she could make it. Very nice. Okay, guys, let's just hit this. So as I go over this, so please make sure you kind of ask questions because it's really crucial for us to kind of see, make sure that we really understand what's going on behind the scene here. So let me just try this one more time. There you go. Turn on the light. Yeah. So chapter 13 is about vector value functions. Remember, these are the functions. Domain is all real numbers and the range is a vector. And this is how they look like in 2 and 3 dimension. Notice the components of the vector, they are functions themselves. Do you see it like f of t, g of t, f of t, g of t, h of t, and so on and so forth. The whole idea behind this chapter is these kind of equations are used in physics classes when you're describing the motion of a moving object on a path, and that path happens to be the graph of these kind of functions. So vector value functions, their graph is always a curve, yes? Either on the x and y plane or in three-dimensional space. However, the beauty of these curves is they are not just curves, they are orientable, meaning they have directions, correct? So they are like orientable curves, correct? Now, either you can what? Show the functions vector-wise, or you can show it parametrically. So these are parametric equations of the what? Vector value function, like in this case in 3D. So these are like examples, like in 2D, I have what? X and Y components. So notice f of t. I'm just reviewing from what we did last time, and that's g of t. Whereas this guy is f of t, g of t, and h of t. The thing you should remember is the graph of these vector value functions, rain or shine, they're always a curve, either in R2 or R3. And also they are orientable, meaning they gotta have a direction, because that would indicate what? Whether the path is increasing or decreasing. I mean, what is the direction of the path? In other words, if this object is moving, is it moving like left to right or right to left or down up or up down? I mean, how is this, what is the direction of this moving object? So primarily that's the reason we are learning this section, so we can do those problems in physics and engineering classes where we're dealing with motions on a path. One of the application of this is those projectile problems. Remember, like you throw an object up in the air, let's say with an angle of like 30 degrees with the horizontal. So you want to know how high the object has gone up in the air. What's the maximum height, and when would the object hit the ground, and when it hits the ground, what's the speed of the object at impact. So that's basically what we did last time. So I did few graphs for you last time. Those of you who were in live session, you notice how I graph a vector value function in 2 dimensions. One way is construct a table, find, come up with values of t on your own, and then find the corresponding values of x and y off of the vector value function. Remember, every time what? You choose a value for t, you are generating a vector, okay? Like at 0, when t is 0, the vector is what? 0, comma 3, which is this guy right here. This is the vector I generated. Do you see it? But the tip of the vector happens to be a point on the path. So every time what? You give a value for t, that generates a what? A vector, because that's what it is. Vector value function is a function whose domain is all real numbers, but the range is a bunch of, it's a vector. But the tip of those vectors kind of what indicates, if you connect the tip of the vectors, that would construct or constitutes what? The path of the motion. In 2 dimensions, either you can construct a table or you can eliminate the parameter if it is possible. Remember, t is called parameter. In physics classes, that would be like the time, and these are called what? Position functions. In this case, because I'm dealing with sine and cosine, I know sine squared plus cosine squared adds up to 1. Somehow I manipulated the equations, and lo and behold, I got rid of the t. So either you can what? Directly what? Plot points and see where the corresponding vectors lie on the path, or eliminate the parameter t and convert the equation into Cartesian so you can recognize the what? Equation. In this case, that's the equation of an ellipse, which has the major axis along the y-axis and minor axis along the x-axis. When it comes to 3 dimension, I'm afraid not much we can do. We just have to plot points. But it just so happens in this case, if you remember from last week, all 3 functions are linear functions. That means the powers of t happens to be 1. You and I, we both know that's the parametric equation of a straight line, which means this is a line in a space which goes through the point 0, 0, 1. That's one of the points, and it's parallel to this vector whose components is 1, 2, 3. Do you see it? Or I should say 1, negative 2, 3. So here's the point right here. Here's the vector which the line should be parallel to, so I draw the line, and lo and behold, there it is. But before I leave the graph, I need to find its direction. How do you find the direction? You know, start with t equal to 0, and then increase the t, let's say t is equal to 1. Let's say t is the time. Where would be the initial position of the object on the path? By replacing the t's in the parametric equation with what? 0. It looks like it will be right here. 1 second later, where would be this object be at on the path? Well, 1 second later, you replace the t's with 1, and lo and behold, it will be right there. So looks to me, the path is going this way. So please remember, even though the picture is a curve, but it has to be orientable. That's one of the beauties of graph of vector value function. Let me see if there is anything concerning, do we have a quiz tomorrow? We don't have a quiz. We have a test coming up a week from this Thursday. The quiz, I mentioned I will make a fake quiz. Not that there will be a math problem on it. It will be like a couple of questions like, what's your name, kind of a deal. I just want to make sure you guys know how to scan the pages and, you know, make a single file and, you know, kind of like upload it on Blackboard in PDF format. It is just a test to see if you guys can upload. exam. So a week from this Thursday when we have a test, so we won't run into technical problems. Okay, so so if the vector value function is in what? In 3-dimension, so then you would have something called space curve, correct? Space curve. And in this case, due to the nature of the way the equation is, this is a very famous function, and the graph is called helix, which looks like a spiral up along the z-axis. So these are all called, this is like a space curve, but it has a name, it's called a line. This is also a space curve, which has a name called helix. Do you see it? So we did that. The other thing which we did last time was finding the domain and the limits of these vector value functions. So let me just remind you, the domain for 2-dimensional vector value functions was intersection of these two domain functions. The domain of the what? A vector value function in R3 was the intersection of the domain of these 3 individual functions. In other words, you have to find the common values of t, which what? Which makes each of these functions a defined function. So the way we did that, if you remember, it goes something like this. Suppose the question is find the domain of this vector value function. Of course, we are in R3. How would you do this? Correct? Remember, this is your f of t, this is your g of t, and this is your h of t. And the question is find the domain of this vector value function. To find the domain of vector value function, I need to find the domain of f, domain of g, domain of h. So I gotta find the domain of each of these components one at a time, yes? What is the domain of natural log of t plus 1? So it's all values of t such that, does anyone know what the domain of natural log of t plus 1 is?
-1 to infinity, not including -1.
Very good. Excellent. Thank you. Thank you so much. So there you have it. Why? Because this is called the logorand, and the logorand cannot be 0 nor negative. Okay? So, so if you would have graphed this, the graph would it will look something like, let's say, this. Do you see it? So the domain is all values of what? T greater than -1, but not equal to -1. Do you see it? So, so we have a natural log of 1 is 0. Oh, that's not right. Sorry about that. So that would be like -1. And the graph would be like something like this. Sorry about that. Because if you set t is equal to 0, natural log of 1 is 0, so the graph goes through 0, 0. But at -1, you have asymptote, vertical asymptote. Anyways, what would be the domain of this guy? T over square root of 9 minus t squared. Any idea, guys? What is the domain of this guy? T over square root of 9 minus t squared. Yeah. Any idea?
-3 to 3.
I'm sorry?
-3 to 3.
-3 to 3. Let's see now. Okay, so this would be all values of t such that. Notice, because this guy is in the denominator and it's under the square root, so I want to make sure that guy is positive. And I can't set it equal to 0 because if this guy is 0, that blows up the fraction. So that's all I got. So if you factor this out, that's difference of 2 squares. So you get something like this. So on the number line, so you would have, let's say, 0, -3, and 3. So if you set these guys equal to what? 0, one at a time, these are critical values. So now you pick a test point to see what value of t makes this guy positive. Suppose I pick 0. If you stick 0 here, 9 minus 0 squared is positive. Therefore, you do have an answer here. So as the gentleman mentioned, t would be somewhere between -3 and 3, excluding 3 and -3. Finally, this guy is an exponential function. You and I, we both know the answer is what? All real numbers. So this is like is an element or member is an element of, and this funny notation is real numbers. So that's what we got. But now we have to take the intersection. In other words, yes, true that the domain of this guy is greater than -1, this guy is -3 to 3, this guy is all real numbers, but I need common values which satisfies all three of them simultaneously. So what you do, you kind of graph these guys on a number line. Let's say you got 0, -1, imagine this is -3, and that's +3, correct? So the first guy is what? Greater than -1, so there goes the domain of f. The second guy says what? You're going between -3 and 3, but excluding -3 and 3. And the last one says you are covering the entire number line. But exactly where about what? These three arrows intersect. Can you all see it? Does anyone see where these three arrows intersect? Sorry?
-1 to 3.
Absolutely, right here, right here. So the domain of the entire function, what? Of r of t is all values of t such that t is between -1 and 3. This is the final answer. Do you all see it? So that's how you find the domain of a vector value function. Find the domain of individual components and take the intersection. Correct? We good? Yeah? All right. So with that said, then how would you take the limit? Well, to take the limit, let's say t is approaching to a constant, like say a, okay. What you do is you go inside, you push this limit into the what? The vector notation, and you simply take the limits of each components, but at the end of the day, you get what? A vector, correct? Just like the example we did last time. So you had this, the question was, what is the limit as t approaches 0? So the answer is this. The closer t gets to 0, the closer this guy gets what? This function gets close to this vector. I think this is where we stopped, you know, derivative. So let me just zoom so you guys can see, then we go from there. Suppose you have a path which is orientable, of course. Let's say this is the direction, and it's a smooth path. What's the definition of a path to be smooth? Well, we will see this later, but let me just give you a heads up. A path is said to be smooth if r prime of t is never equal to what? 0 vector, right? Never equal to 0 vector for any t. For any t. That's the definition of a curve to be smooth. In other words, there is no break, there is no sharp turn on the curve. So this is the definition of a smooth curve. Excuse me. If the derivative of the vector value function is no over 0 vector, this is not 0 the number, 0 the vector for any t in the domain of what? R of t, then that function, the graph is smooth. Let's say this guy is smooth. So you have this position vector R of t. Imagine we increase the t by the amount of h. So h is increment of t. In other words, that's how much t has been increased. This is also position vector. So if I kind of get the tip of these vectors right there, P and Q, and connected. That line is called, this vector is called secant vector. Secant, not secant line, but secant vector, meaning PQ is called secant vector. So what is PQ equal to? Well, notice OP plus PQ is equal to OQ, so these are vectors. Therefore, PQ is OQ minus OP. So this is how you find the components of the vector what? PQ, or this is how you express PQ in terms of vector notation, you know. So, so if H is positive, which it is, because that's the amount of increment, not decrease, but increase. So let me go back. So if you multiply this guy by 1 over H and H being positive, so this guy still has the same what? Direction as PQ. Now, the smaller the H gets, what? The closer what? Q gets to what? To point P. And eventually this secant vector becomes what? Tangent vector. Do you all see it? There it is. Okay, there it is. So this guy, as you move point Q towards point P, the closer you what? Push this point Q towards point P, the closer what? This secant vector gets close to what? Something called tangent vector. Do we all see it? So this is a vector. I assumed H is a positive number. When you multiply a vector by a positive number, that...
Oh yeah, we should probably put that in homework. Have everyone post some study times if they're available.
Yeah, probably should have started doing that, I don't know, a week earlier.
Oh, okay. Nope. Can you guys hear him?
Professor, you're not transmitting your audio. We can't hear you.
Can you guys hear me?
Yes.
Yeah, now
Oh,
we can.
sorry. I was just saying I had a Wi-Fi problem, so I got dropped, and sorry, expect this to happen, you know, technology. And remember I told you don't subscribe to AT&T, okay? So I'll go with someone else. All
Duly
right,
noted.
let me see if there is anything. We can hear you, so we good now, yes? All right. So I was just saying before I got cut off, this guy is the secant vector. Oh, okay, what guy? Let me switch. This guy is the secant vector. We assumed H is positive, increment of T, correct? So therefore 1 over H is still positive. So when you multiply a vector by a positive vector, that does not change its direction, correct? So, so this is still in the same direction as the what? Secant. The reason we did this, so now we can do this. Now we can take the limit of that fraction and let H to approach to 0. When that happens, what? The secant vector becomes tangent vector, and that's the formal definition. This would be formal definition of what? Of derivative of a vector value function. There you have it. So r prime of t, which is dr dt, is the limit of r of what? T plus h minus r of t divided by h as h approaches 0. Almost similar to real value functions. Can you all see it? So r prime of t is called tangent vector to the curve at point P. There it is. This is called tangent vector. Here is r prime. Okay, that's the tangent vector. But then if you divide that tangent vector by its magnitude, you get something called a unit tangent vector. So if this is the curve, here is the tangent vector, r prime of t, let's say at point P. Unit tangent is on the tangent vector, but its magnitude is what? It is 1. What's so good about unit vector in what? Physics classes? You know, this unit tangent vector. The direction of the unit tangent vector indicates the what? Direction of the motion of the what? Moving object on the path C. So this guy always points to the direction of the motion, you know, this unit vector. Later on, like in about 15 minutes, we will also see, oh my goodness, there is one more vector called unit normal vector. And that always points to this, what? To the direction where the curve, what? Bends. In other words, or it turns. So this would be the direction where the what? The path makes a turn. Do you see it? And that's called unit normal vector. Okay, normal vector. We also have one more vector in motion problems. This is called binormal vector. So this guy is unit binormal vector. And guess what's so good about that? It's perpendicular to both normal and unit tangent. And this kind of frame in physics classes is called TBN frame. In other words, anywhere on the path, what? The object is what? Subject to these what? To these 3 vectors: unit tangent, unit normal, unit binormal. Okay? So this guy points in the direction of the motion. This guy points in the direction where the path turns, not bends, but makes a turn. And this guy is perpendicular to both of them. And this binormal vector in physics classes is used to find something called torsion. Does anyone know what a torsion is?
It's the
Yes.
measure of twist.
Twist, yes. Very good. Thank you, thank you, thank you. Yes, indeed. It's a measure of twist. As curvature, which we will see that today, is measure of bend, but this guy is associated with something called torsion, which is measure of twist. Twist is not the same as bend. Those are 2 different kind of what ideas. Okay, but for practical purposes, we never use this limit, as we never use the definition of derivative for real value functions. For practical purposes like homework assignment, all we do is what? Go inside the vector and what? Take the derivative of each component one at a time. So we never ever use the definition. This is the formal definition, just to make sure we know why are we doing this, okay? So the bottom line is, if you have a vector value function, you want to find its derivative, just take the derivative of the what? X component, Y component, and in case of what? 3-dimension Z component, you are good to go. So if this guy is a position vector, so if I take the derivative of that, so derivative of cosine is negative sine, sine is cosine, e to the t, that's velocity. So if this is position vector, so this guy is called velocity. And if I take the derivative of the velocity, I get something called what now? Acceleration, correct? Acceleration is how fast velocity is changing. Velocity is how fast the position is changing, and they're all with respect to time. Incidentally, we also have what? Speed. Speed is the what? Magnitude of the velocity, correct? Speed is a number. Velocity is a vector. It has a direction, correct? So keep that in mind. Speed is magnitude of the velocity, which is a number. When you say you're driving your car 55 miles an hour on 55 miles an hour, that's the speed. But the minute you mention I'm driving 55 miles an hour on 405 north, that's velocity, yes? So that's basically where we are with that guy. So now that we know how to take the derivative, so the next natural question is, how do you find the equation of a tangent line to a space curve? How do you do that? In other words, let's say this is a curve. Let's say this guy is my so-called tangent line. Tangent line. I like to find the equation of this tangent line. How would I do that? Okay, how would I find the equation of a tangent line to a what? Space curve, which is orientable at a specific point on the curve. Okay, let's get back to this guy. Remember that guy is, that's the helix, okay, which looks like this. Let's say this is at t is equal to pi over 2. I like to know what's the equation of this tangent line is this guy right here. Okay, at that point. So here is the vector value function. What am I supposed to do? Because I need a point like x0, y0, z0, and I was not given, but I have but also instead of point, I have been given the instant where what? I will have a tangent vector on the curve. So this is like pi over 2 seconds. So what you do first step is find the point, find the x and y and z component of the point. How? Go back to the vector value function, replace the t's with pi over 2, and lo and behold, here's your point. Because that would be like cosine of pi over 2 is 0, sine of pi over 2 is what? 1. And when you replace t with pi over 2, you get pi over 2. So you got your point. Now you know at pi over 2 seconds, the object is located at 0, 1 pi over 2. Now I need the direction of this tangent vector. Step 2, take the derivative of what? Of vector value function. So this is the same as derivative of r with respect to t. Why? Because you're trying to find the what? The direction of the tangent vector, which is r prime of t. Well, take the derivative of cosine and sine and t, you get what? Negative sine, cosine, and 1. Evaluate this at what? Pi over 2, you get this. So this is the direction of the tangent vector. Okay? So I got its direction. I got the point where I want that tangent vector to be drawn on the curve. So because I'm writing the equation of a line, so I use the parametric equation of a line. So this is called parametric equations of a space line, which is this guy. If you remember from 12.5, the equation, this equation says, hey, the line goes through this point and it's parallel to this vector right here, the coefficients of t. Well, guess what? My ABC is what? The components of r prime evaluated at pi over 2. My x0, y0, z0 is what? Evaluating the function itself at pi over 2. Here's my point. So I'm going to stick those numbers in my parametric equation of a line. And I'm going to let people know that t goes from negative infinity to infinity. And lo and behold, I have the equation of the tangent line. There it is. Keep in mind not to confuse the equation of a line with equation of a plane. Equation of a plane doesn't look like in parametric form. Yes, be careful. Now, either you can leave the answer this way, parametrically, or you can write the answer in vector notation. So this is your option 2. How did I go from here to here? Well, here's my x component, here's my y component, here is the z. I just copied these guys over and put them inside the square bracket, and I still have to tell people t goes from -infinity to infinity. Keep in mind for line segment, what? T goes from 0 to 1. You all see it? Let me just stop right here, make sure we're all on the same page. How are we doing on equation of a what? Tangent line to a space curve. So I just found the equation of this line right here. I just found out what the equation of that line is. It's right here. X is -t, y is 1, and z is pi over 2 plus t. Remember, this is my ABC, and that's my point. And here is my parametric equation for any line in space. Let me just stop, make sure you're all with me. If there is any question, please let me know. I can elaborate before I show you something else. Question. How are we doing? Are you following all? Are you following these topics? Is there any issue? Is there any problem? Just like any other class, guys, if you practice these and do your homework, you should be okay. I know it's different. I know we have never seen these unless we repeat in the course, but it's not impossible. You know, people prior to you, students prior to you took it, passed it, and they're on their way to graduate, or they
I
already
think his
graduated.
Wi-Fi went out
You
again.
can do it
Yeah.
too. So it is not impossible. It's just brand new language we are learning 1 week at a time. Any question? So here is a fascinating problem right here. You got two aircrafts travel through the space along two different paths. Okay, wow. I guess today is not the day, is it? I keep getting dropped off from Wi-Fi, sorry. Can you all hear me? Let me see, what do we have?
Yeah, we can hear you.
Okay, return. Okay, Jacob. All right, so let's get back right here. Notice you got two aircrafts travel through space along two different paths, or mathematically curves. This is the path of the first aircraft. This is the path of the second aircraft. Question, do the aircrafts collide? Are we going to have a major accident up in the air? Let's see. What do you think? What should we do? Any idea? Two aircrafts travel through the space along two different paths. In other words, this is what's happening. Here is the path, C1. Here is the path, C2. This guy is given by what? By R1 of t, and this guy is by R2 of t. So these are the paths of two aircrafts up in the sky. Do they collide? Are we gonna have an accident up in the air? When do they collide? Under which condition two aircrafts will collide up in the air, knowing the equation of the paths? What do you think? Okay, don't tell me if it is a cloudy sky or it's raining. Talk to me mathematically. Under which condition these two objects will collide? let's say this is airplane number 1. This is like airplane number 2. When do they collide? Under which condition?
When R1 of t and R2 of t are equal?
Is that it?
I believe so.
What if this guy goes through this point at 4 p.m.? The second aircraft goes through the same point at 4:05 p.m. They don't collide.
They have to be equal and t has to be the same.
They have to what? Have what? Same path and same time. So therefore, in other words, they can only collide if they what? Go through the point at the same time and what? Go through same spot at the same time. Okay, you are right, Nick. So what we do, we set these guys equal to each other and solve for t. Okay, so how? How do you set two vector function equal to each other? Well, you set the x component equal, then you set the y components equal, then you set the z components equal. You will have three equations, one unknown, and this is how they look like. But from the first equation, t is equal to -1. But if you stick -1 in equation 2 and 3, it doesn't satisfy these equations. Therefore, the conclusion is the aircrafts do not collide. Because I couldn't find a common time where both aircrafts goes through the intersection of these two paths. Notice I solved the first equation for t. T came up equal to -1 when I set t is equal to 1 plus 2t. You know, when I equated the x components, I got this. But when I stick that to equation number 2 and 3, it didn't satisfy. So the conclusion is no, they don't collide. The next question is, do their paths intersect? In other words, do they go through this point, this intersection point, at two different times? How would I do that? This guy was what? They going through the point at the same time and what? Same path. But this one says it goes through the point P, but they don't go or pass through that point at the same instant of time. So they just what? Their path intersect, not the aircraft themselves. So what do I do now? Any idea? So here, same path, same time. Here, same path, but different times. Otherwise, they collide. So what do we do? So if they are going to have different paths, so I'm going to call this what? S. So that will be time for what? R2. And I'm going to keep that guy, the first guy, as T, time for R1. I can't call both of them T because I'm trying to see, are they going to what? Would their paths cross, but not necessarily at the same time? So I can't call these T's anymore. So I'm going to call one of these paths time S and the other path time T, correct? Let me see if we have any comments. Do we just check their domain? I'm afraid not. I'm trying to see, how would I say this? What value of S and T makes these guys equal? So notice it's kind of independent from domain. So I'm trying to find out what value of S and T makes these two vectors equal. Because that way I can say, aha, aircraft number 2 passed that intersection point at such a time, and aircraft number 1 passed the same intersection at a different time. So notice it's kind of independent from the domain. Do you see it? So the bottom line is, go back to what? R2, replace the T's with S. Write this as 1 plus 2S, 1 plus 6S, 1 plus 14S. Because you're trying to what? Match the paths, but not the times, you still have to what? Set the corresponding components of these two vectors equal. You know, x's with x's, y's with y's, and z's with z's. And this is what you get. So you get 3 equations. Can I just zoom in? 3 equations, but 2 unknowns. Okay? So what do? Take the first 2 equations and eliminate S and then solve for T. So this would be like T is equal to 1 plus 2S, T squared equals 1 plus 6S. Okay, so what I did, I multiplied the top equation by -3, so that way I can cancel the S's. Do you see it? So what did I do? I only took equation 1 and 2. When I did, I ended up with a quadratic equation, so I have 2 answers. Either T is equal to 1 or T is equal to 2. If T is equal to 1 from equation number 3, which we forgot to choose, S would be 0. On the other hand, if T is equal to 2, S would be equal to 1/2. So the bottom line is as follows. Either they will what? Hit each other at T is equal to what? 1 second for aircraft number 1, or 2 seconds, that's for 1. But when it comes for aircraft number 2, the time is either 0 or 1/2. Do you see it? So I guess they intersect at 2 different times. For aircraft number 1 is at, I don't know, 1 o'clock and I don't know, 2 o'clock. This guy is at noon and let's say 12:30. But they do go through that intersection point at 2 different points. So now the job is, what is that point of intersection? Well, either you go back to what? R1, replace the T's with either 1 or 2, or go to R2 and replace the S's with 0 and 1/2, you still end up with these 2 points. So the paths intersect twice. So at these 2 points, they intersect each other at these corresponding times. Do you see it? Remember, the difference between part B and part A is, in part A, they collide. In part B, they go through the intersection point without colliding. Why? Because they don't go through the intersection at the same time. It occurs at different times. Do you see it? So in this case, because we had 2 points, so the idea is path intersect twice. So path intersect twice, right? So I thought I should bring that to your attention, give you an idea what is going on. Why do I care about vector value function? It shows up in upcoming classes, and our class at the end of this chapter, we will do some trajectory problems, and you will see the path is defined in terms of vector value function. Let me see what we got here. Do we just check their domain? No, but yeah. Did you like this problem? This was from aerospace class. Do you see it? And when do we do this kind of problem in that class? Like the first day, because the prerequisite for that class they take is Math 2140. So there you have it. Okay. So if you're still with me, I'd like to introduce antiderivative of vector value functions, which is section 13.2. How we doing? Should we take a 5 minutes break before we hit this section? Are you guys still okay, or do you need a break? You good? Are you okay? Can you stand 2 hours straight of math, or you had it? We good? Anyone? Any sign, please? Let me see. Maybe a water break. Yeah, why don't we? A water break. Go ahead. Go ahead, please. I'll wait. Thank you. I forgot. Yes, thank you. Okay, so now what? Evaluate this guy at the upper limit. So that will be sine of pi over 2, which is 1. Cosine of pi over 2 is 0. And that will be like pi squared over 4 minus sine of 0 is 0. Cosine of 0 is 1, but there is a negative, and that guy is 0. So evaluate the antiderivative at the upper limit minus at the lower limit. Now subtract the vectors. When you do, you get 1. What is this? 0 minus minus 1. And that will be pi squared over 4, which is the final answer. Notice the final answer is still a vector, but there's no c because this is what? A definite integral. The only time we get a constant c if there is an indefinite integral. Do you see it? So the question is, where would you use this? Well, in application problems. Like what? Like, suppose the question is find r of t if r prime of t is 2t, 3t squared, square root of t, and we have an initial condition. R of 1 is equal to 1, 1, 0. This is called differential equation. Differential equation. Why is it called differential equation? Because you have a derivative. They want you to find the original function. So every time an equation has a derivative in it, that's called differential equation. As a matter of fact, that's the topic of my next class starting at 7, which is 2240. Part of the course is called differential equation. So differential equation is an equation which has a derivative in it. What is the objective of these kind of equations? Find the original function, correct? Let me see if there is any comments. Can you also use integration to find point in the past or how much you have displaced? Of course you can. Of course, yes. And that's basically what this is all about. I mean, by integrating, we're trying to find the original function. Once I find the original function, then I can predict what's going to happen in the future or what has happened in the past. Yeah. So let's do this, shall we? So remember, I'm trying to go from r prime of t to r of t. So what it takes to go from here to here is antiderivative, not derivative. So I'm gonna say r of t is equal to antiderivative of r prime of t with respect to t. So I'm gonna get what? 2t, 3t squared, and I'm going to write that as t to the power of 1/2 dt. Okay, so r of t is equal to, guess what? This would be antiderivative of 2t dt. Excuse me, guys. Antiderivative of 3 squared dt. Antiderivative of t to the 1/2 dt. Remember, you can push the integral into the what? Vector. Now, r of t is equal to, what is it? T squared. What is that? T cubed. What is that? T to the power of what? 3/2 divided by 3/2, which is 2/3. But don't forget you have a constant. But the constant is not a number, is a vector. Keep that in mind. Why do we have this condition for? Well, that's an initial condition. Usually you are given initial conditions so you can find out what C is. In this case, it says when T is equal to 1, R is equal to 1, 1, 0. So what you do, you replace R with 1, 1, 0, and all these T's with 1. So you get 1, 1, 2/3 plus C. So what did I do? I replaced T's with 1 and r of t with, excuse me, 1, 1, 0. And that's what I got. Now what do I do? Move this guy over to the left side and subtract it from this vector. Okay, like so. So what do you get? 1 minus 1 is 0. 1 minus 1 is 0. 0 minus 2/3 is negative 2/3. There goes your C. Is that right? Now what? Now go back here and replace the C with 0, 0, negative 2/3. Okay, so what do I get? I get r of t is equal to what? T squared, t cubed, 2/3 of what? T to the power of 3/2 plus C, but I know what C is, 0, 0, negative 2/3. Okay, now I need to add these vectors up. Okay, add them up. Okay, how do you add two vectors? Component-wise. So what is R, the position vector? It is t squared, t cubed, but it's 2/3 of t to the power of 3/2 minus 2/3, because you gotta, add negative 2/3 to this guy. Here is the final answer. Do you all see it? Okay. Any question on that? Is that right? You all see it? How did I pretend this guy was velocity vector? So velocity was given with the initial condition, and lo and behold, I got the position vector. Do you see it? Position vector. Do you all see it? So I went from velocity to position. Sometimes they give you acceleration, they want you to find position. So you have to what? Repeat this process twice. And that's basically what we're gonna do next. And that should do it for tonight, even though we were supposed to go over next section, but that's okay. Can I just quickly show you a word problem? So that way you guys can see where do we use integration. Those problems are called projectile motions, okay? This kind of word problems are, these kind of motions, I should say, they describe how an object fired at some angle from an initial position and acted upon only the force of gravity, okay, moves what? In vertical coordinate plane. So we're going to make a ton of assumption when we do these kind of problems. Those assumptions are: ignore the air resistance, which is called drag force. Remember, air resistance reduces the speed of the motion. So if you consider that, then the equation becomes a bit complicated. Also, we're going to assume the mass of the object is constant. So the mass doesn't change. So according to Newton's law of motion, the force acting on the object is proportional to the acceleration, meaning F is equal to ma. But both of these guys are vectors. But the only force acting on the object is gravity, which is negative mg. So the assumption is going up is positive, going down is negative. So this has to be negative mg. In other words, this guy, which is the force due to the gravity, has to offset this guy. In other words, this is what's happening. ma has to be equal to negative mg. So remember, a is the vector. This is acceleration, correct? So notice r is what? Position vector. Is that right? V is what? Velocity vector. Okay. And A, which is also a vector, is called acceleration. All right. So there. So if MA is equal to minus MG, because we assume what object has a constant mass, so I can divide both sides by M. So Mayday, Mayday, we have a problem. Notice on the left side you have a vector, on the right side you have a what? Number. Remember what G is. G is what? 9.8 meter per second squared, that's the gravitational constant, or 32 feet per second squared. So this is a number, so no can do. I cannot set A equal to negative G. It doesn't make sense, because on the left side you have a vector, on the right side you have a number. So somehow you gotta convert this guy to a vector. Because the gravity is what? Along the vertical axis. So instead of writing negative G, we're just gonna write that in vector notation, 0, negative G. So now it's a vector whose x component is 0, but the y component is negative G. Now that this makes sense. So now this is a vector as well. So you can set a vector equal to a vector. You cannot set a vector equal to a number. Do you see it? And also the assumption is this is linear, what, motion. So the object goes straight up and then goes down. Yes? All right. Sometimes you may have an angle, and that would be like projectile kind of a problem. But remember, acceleration is what? Second derivative of the position. So the m's, once again, they cancel. Okay, cancel the m's. So now to go from acceleration to what? To velocity, I have to take what? Antiderivative of what? 0, negative g with respect to t. Once I get velocity, then I can take one more integral to get my position vector. And then I have to impose the initial conditions to get all the c's out of my way so I can answer their questions, correct? So this is basically in a nutshell what we're gonna do when we are asked to solve a free fall type of problem. Free fall meaning the only force acting of the object is the what? Gravity, nothing else. So also known as projectile motion. So if you don't mind, I'd like to show you a problem, but first let me make sure you understood what we are going to do. We are going to solve a free fall problem. We're going to make an assumption like what? Does anyone know what the drag force is equal to or proportional to? So this notation is proportion. Does anyone know what the drag force, which in this case is air resistance, is equal to? Have you ever experienced with this in any other classes? If you could, would you mind sharing with us? What sorry?
I know there's a coefficient of drag that is like based off of the shape of the object.
Shape and the speed of the object. So for the low velocity and the small objects, this would be proportional to the velocity. Okay. And on the other hand, if the object is what? Large and high velocity, this would be proportional. These are constant of proportionality to square of the velocity. So for low objects, for low speed and the small objects, when we talk about small objects, we're talking about paper clips. So the drag force is proportional to the velocity. For heavy objects, we're talking about tennis ball, the drag force is proportional to the square of the velocity. Just something on the side, I thought I should bring it up so you guys can kind of go have that in your archive. So here's the problem. A projectile, this is very classical problem. A projectile is fired with an initial speed of 200 meters per second. That's initial speed, not the velocity. An angle of elevation of 60 degrees. So what does that mean? That means this. Incidentally, when this experiment took over, we were on the ground. In other words, the initial position was 0. So the experiment was conducted when what? The cannonball was on the floor. So we are, ignoring the height here. So initial velocity, the speed was what? The speed initially was 200 meters per second. What does that mean? That means what? The magnitude of the initial velocity is 200 meters per second. So remember this guy right here, V of 0 means initial velocity. Initial velocity. Well, we were told what the speed is. Speed is the magnitude. Alpha, which is this guy, is the angle of elevation. Angle of elevation. Okay, so in other words, this is how you shoot the ball up in the air in an angle, 60 degrees. Okay, and question is, find all sort of goodies about this object. First, what is the range? That's also known as downrange of the particle. Range is how far the ball traveled on the floor before it hit the ground. This is the range. Also, what's the maximum height? This is the maximum height. Also, what's the speed at the impact? Right here, when the ball hit the ground, what was the speed? So we need to what? Before we answer any of these questions, the main part of the problem is how do you go from acceleration to position? So let's do that, shall we? Here we go. So I'm gonna take you through the steps. Please pay attention. Make sure you get it. If not, let me know. We decided M, what was it? A, this is function of time, equals minus mg. But I can have a number. And so if I divide both sides by m, I get A of t is equal to minus g. But this is a number, so I can't have that. So I'm going to write it in terms of what? Vector. So this is a vector, that's a vector. I'm going to call this guy position vector. Position vector. That's the arrow. This is called velocity vector. Okay, velocity vector. This is called initial velocity. This is initial velocity. Velocity. This is called what? Initial position. Initial position. Those are the notation I'll be using. I think we are dealing with meters, so in this case, G will be 9.8 meter per second squared. So it's a constant of gravity, yes? In English system, it will be like what? 32 feet per second squared. Okay. Remember, acceleration is second derivative of the position with respect to time. In other words, acceleration is r double prime of t. If you take two derivative of the position vector, where is it? Right here. Then you get acceleration. Okay, so this is what I'm going to do. I'm going to start with acceleration, work my way to velocity, then work my way to position vector. Each time I have to take the integral. And each time I'll have a different constants as a vector. Okay, so let's do it. So velocity is equal to antiderivative of acceleration, but acceleration is a vector, which is 0, negative g dt. Okay, so what would this be equal to? 0 minus gt plus c1, a vector. Okay. Now, remember, this was the situation. The magnitude of the initial velocity, what was it equal to? 200 meter per second. And alpha was what now? 60 degrees. So what is the initial velocity equal to? Okay, remember this is the magnitude of this guy was 200 meter per second, but it made an angle of with the horizontal 60 degrees. So what would be the component of the initial velocity? It would be 200 times cosine of 60, 200 times sine of 60. In other words, I have to find the x and the y component of the initial velocity. Correct? So what is this? This is 200 times 1/2, and this is 200 times the square root of 3 over 2. So that will be 100 and 100 square root of 3. So what is this? That's my initial velocity. So my initial velocity is 100 square root of 3. Correct? So this is my initial velocity. That guy was what? Speed. So now, this is my initial condition, so I'm going to impose this right here. Remember, my velocity came up to 0, negative gt plus c1. So I'm going to impose this initial condition, IC, to find c1. How? This guy says when t is 0, v of 0 is 100 square root of 3. Is that right? So I'm going to go back here, replace this guy with 100 square root of 3, replace the t's with 0. And I'm going to solve this equation for vector c1. It's not a number, it's a vector. Okay, so c1, if you subtract this guy, subtract this from this, you get the same vector back because that's 0, 0. Okay, there it is. Go back and what? Replace this guy with 100, 100 square root of 3. So therefore, the velocity at any given time is 0 minus gt plus 100 square root of 3. Is that right? So what did I do? I impose the initial condition so I can find C1. Once I find C1, I go back and substitute here so I can tell what the velocity of the object is at any given time. But first, I need to add them up, add these guys up. So what do you get? Velocity of the object is what? 100, 0 plus 100, comma, 100 square root of 3 minus gt. So add these components, then add those components, and that's what you get. And this is so many meters per second. Okay, are we done? No. Why not? Because now I have to find the position. How do I do that? Well, position is obtained by taking the antiderivative of the velocity. So position r of t is equal to antiderivative of the velocity with respect to t, which is antiderivative of 100 square root of 3 minus gt with respect to t. Is that right? Okay, let's take the antiderivative. What do we get? We get r of t is equal to what? 100t, 100 square root of t minus gt squared over 2 plus c2. So take the integral of 100 with respect to t and take the integral of 100 square root of 3 minus gt with respect to t. That's what you get. Do you all follow? Do you all see what I'm doing? So now I have to find C2. Because the initial position was on the floor, because they didn't say the guy went up on balcony and threw the object, it was done on the floor. So by default, this means R of 0 is 0 what? Meter. Okay, so this is my initial what? Position. The experiment was conducted when the object was on the floor. So by default, R of 0 is 0, unless they stated otherwise. Do you see it? So go back to this equation, replace, excuse me guys, this is supposed to read 0, 0. Replace R of 0 with R of t with 0, 0, and all these t's with 0. So C2 is going to be 0, 0 as well. Okay, you all see it. So now we're almost there. So I'm going to go back here, replace this guy with 0, 0. So that would be 100t, 100 the square root of 3t minus gt squared over 2 plus 0, 0. Well, when you add a 0 to a vector, you get the vector itself. So this is, lo and behold, my position vector for that object at any given time. Now I can answer their questions. So this is basically where we want to get. What's the first question? The first question is, what is the range? The range, also known as downrange of the projectile, which means how far horizontally the object traveled, and hit the ground. In other words, what's the distance from here to here? Remember, this is the object. Let's say it's like a tennis ball or something. So this is called the range or downrange. It's the distance from where the object was fired to the point where the object hits the floor. This is called range. Okay, how do I find that? Well, to find that, I need to evaluate the x component. This is called the range of the projectile. But what is t? How do I know what t is? Does anyone know? How do I find t? Yes? How do I know how long it took for the ball, after it was fired, to go through this path and hit the floor? How do I know the amount of time it took for the ball to hit the floor? How would I find it? Anyone see it? Yes, no, maybe.
Set the y component equal to
Yes,
0 and find.
yes, precisely. When the ball hits the floor like this, at this point, there is no y. Y is 0. So go back to the y component of the position, set this guy equal to 0. So set y component of r of t equal to 0 and find t the time. In other words, set 100 the square root of 3t minus g over 2t squared equal to 0. Don't forget, g is 9.8 meter per second squared. So we know what g is. Okay. So when you do this, you factor out a t. One of the t is equal to 0. That's like when the ball was on the floor to begin with. So I need this guy, 100 square root of t minus g over t. So t is equal to 100 square root of 3 over g over 2, which this comes up to 35.3 seconds. Remember, you're supposed to replace g with 9.8. Okay, this is when the ball was on the floor. This is how long it took for the ball to hit the floor again. Okay, now go back to the range, which is 100t. The x component is called the range. And evaluate this at t is equal to 35.3. And that gives you 3,535 meters. So there goes the range. Okay, in other words, from here to here is 3,535 meters. Okay, how do I find the maximum height? So this is maximum height. How do I find that? How do I know what this height is? Any idea? Maximum height. Yes. What do we know about maximum point on a curve from Cal 1, from first semester calculus? How do you find the maximum? Anyone?
You set the y component of the position vector equal to
You
Sure.
mean velocity.
or velocity. Sorry, yeah.
Velocity. So set the y component of the velocity equal to 0 because this is the tangent vector. Tangent vector to the path is called velocity. So set the y component of the velocity equal to 0 to find out how long did it take for the ball to reach its maximum height. So yes, go back to the velocity. What was my velocity? It was, you remember, what was my velocity? 100 comma 100 square root of 3 minus gt. That was meter per second per second. Set the y component equal to 0. So set 100 square root of 3 minus gt equal to 0 to find out how long it took for the ball to reach its maximum height. So in this case, it's 100 square root of 3 over g. Is that right? So what would that be equal to? Well, that would be roughly equal to 17.7 seconds. Okay, remember I'm replacing g with 9.8 meter per second square. So 100 square root of 3 divided by 9.8 gives you 17.7 seconds. So now, that's the time. How would I find the maximum height now? Okay, that's not the maximum height. That's the time for the ball to reach its maximum height. How do I find the maximum height?
Plug it in for the
Plug it
y
in where?
component of the position.
Yes, y component of the position right here. So take what? Take, what was it? What was it? Take the position vector. So what? Take the y component of r of t, not velocity, but r of t, and replace the t with 17.5 seconds. What was the y component of r of t? Let's see, 100t, 100 square root of 3t minus gt squared over 2. This guy. So maximum height will be equal to what? 100 square root of 3 minus g over tt squared, but replace the t with 17.7 seconds. When you do, you get the maximum height as 1,531 meters. There, that's the maximum. Okay, notice we're dealing purely with vectors, correct? Okay, one last part. What is the speed? This is part C, speed at impact. Okay, how would I find that? Anyone? Speed at impact.
You know the total time, so
Which took for the ball to hit the ground. What was it?
it was 100 root 3 over 4.9.
Correct, 35.3 roughly, which we got it by 100 the square root of 3 divided by g over 2, which is 100 the square root of 3. G is 9.8 divided by 2 is 4.9. So that gives you this many seconds. Okay, now what?
You plug it into the velocity vector.
Velocity 35.3. So that would give, what was the velocity? It was 100 square root of 3 minus gt. Evaluate t as 35.3, correct? And now what? That would give you 100 square root of 3 minus g times t, but t is the square root of what? What was t, guys? What was t? It was, what was it?
100 root 3 over 4.9.
3 over g over 2. At the end of the day, you get 100 comma minus 100 the square root of 3. The g's cancel. Okay, and this gives you two of these. One of these minus two of these gives you minus one of those. Because remember, the 2 goes up. The g's cancel. The 2 goes up, so this guy becomes 100 to the square root of 3 minus 2, what? 100 to the square root of 3. Then you get minus square root of 3. Okay, that's velocity, meter per second. I was asked to find the speed. What do?
Take the magnitude of that vector.
Of the velocity at that point. Thank you, sir. And lo and behold, this would be 200 meters per second. And that's speed, which is magnitude of the velocity at t is equal to, what was it, 35.3 seconds. And that's a typical example of the projectile problem, which is the application of antiderivative. Do you all see it? Yeah?
I have a quick question on this.
Yes, please.
So what I've learned from physics, I know it's not the same in calculus when you're doing motion problems, the equations aren't the same and all that. But what about like some of the conceptual things, like if you, for instance, if you throw a ball straight up in the air at like 10 meters per second, it's going to come back down at 10 meters per second. Are we safe to like use that in our calculus problems, like for this?
Yeah, I'm afraid not. So we are not going to mix physics with mathematics, although physics uses mathematics, but they have magic formulas there, and we are not going to use any of those. Basically, the whole idea is to implement antiderivative to a vector value function, evaluate the constants, come up with the position vector, and answer the questions. I know there are fixed problems in physics which immediately gives you what? The time the ball reaches its maximum, and so on and so forth. So please avoid those. So on the test, if this shows up on the test, I'm not sure, I will put a comment on next to the problem. Please do not use physics formula. So notice we are kind of simplifying the situation than what they do in physics, but the trade-off is we use mathematics to derive the formulas as opposed to use a fixed formula, stick some numbers, and then lo and behold get an answer, because that would defeat the purpose of this section, which is what? How to take antiderivative of vector value function. Yeah, a lot of assumptions made here, but at the end of the day, we are not going to use any physics formula, nor are we going to use some of the assumptions they use there. So we're just going to go bare minimum, like everything is rosy and peachy. So yeah, because in physics, they also consider the drag force. And once you incorporate, then the equation becomes hard. Well, hard for this class, but in next class, 2240, we deal with it and we incorporate it and we have no problem, but not in this class, no. Yeah, so there you have it. So with that in mind, have a great what? night, and then I will see you all, say, Thursday. So please bring some questions for me so we can, solve those problems and answer your questions during the live session, because that's the purpose of this. I'm just repeating what I have said on the video, pre-recorded videos. Sometimes I do different problems, but most of the time I'm just repeating those. So please watch those videos, and then we should be a-okay. Thank you, guys. Have a good night.
Thank you, Professor.
Have a
Thank
good one,
you, guys.
Professor.
Thank you, guys. Take care.